Hello ladies and gentlemen, in the last video we have seen the mathematical model of ISI and the Nyquist condition for 0 ISI, and we saw that we in the end we saw that xt or xnt should be a delta function. What is this xnt? That is sampled version of xt. And what is this xt? That is the combined effect of the transmitter filter, channel and the receiver filter. That is xt is gt convolution, ct convolution, ht. So when it is sampled, you get xnt, and if this xnt is a delta function, we say there is 0 ISI. Now this condition is a little hard. Now in this video we see the signal design with the controlled ISI. So let me start with that presentation. The speech is organized into the learning outcomes. You will learn the design of duobinary and modified duobinary signals with a controlled ISI. There is limited amount of ISI. That's a controlled ISI. You allow some ISI so that you can have a signal design, a convenient signal design. So the condition that x of nt, that is a sampled version of xt. What is xt? xt is gt convolution, ct convolution, ht. gt is your transmitter filter, ct is the channel, and ht is your receiver filter. Now this condition, this xnt is an impulse, is hard to realize. So instead we go for a relaxed condition. Say xnt equal to 1 for n equal to 0 else. The hard condition is xnt is 1 for n equal to 0, everywhere else it is 0. Now we allow two impulses. Say xnt is 1 for n equal to 0 and n equal to 1. Now earlier in the last video we proved that bn, that is equal to tx minus nt. Okay. Earlier we proved that bn, that is t times x minus nt. So that means bn is t for n equal to 0 and n equal to minus 1, because there is a reversal in time. So bn is t for n equal to 0, n equal to minus 1, equal to 0 else. Therefore b is a bf, that is a Fourier transform of small b, that is t plus t raised to minus j 2 pi ft. Okay, t plus t raised to minus j 2 pi ft. So now there is ISI for t less than 1 by 2w. Okay, my x is bar limited in minus w to w. So consider the case, the limiting case with t equal to 1 by 2w, so that my xf becomes 1 by 2w. This becomes t equal to 1 by 2w. So it is 1 by 2w plus 1 by 2w raised to minus j 2 pi f divided by 2w. So if I take that t or 1 by 2w outside, it becomes 1 by 2w. 1 plus e raised to minus j 2 pi f by 2w, it becomes 1 plus e raised to minus j pi f by e raised to minus j pi f by w. Now if I take out e raised to minus j pi f by 2w from this, it will become 1 by 2w e raised to minus j 2 pi f by 2w into this becomes e raised to j pi f w by 2 plus e raised to minus j pi f by 2w. It becomes a 2 cos pi f by 2w. Okay, the 2 is cancelled with this 2, so it becomes 1 by w e raised to minus j pi f j pi f by 2w into cos pi f by 2w for mod f less than w. Otherwise it is 0. Outside f mod f greater than w, it is 0. Now if I look into this equation for xf, I can compute xt. This is equal to sinc 2wt, because this pulse of width 1 by 2w, so its inverse transform should be a sinc function. So it becomes a sinc 2wt plus sinc 2w. This is multiplied by, this is a pulse of width 1 by 2w in the frequency domain. That is multiplied by e raised to minus j pi f by w. So this is advanced by, this is delayed by a half unit. Okay, This is e raised to minus j 2 pi f by w. So it becomes, this becomes a sinc 2w t minus half. Okay. So this is a kind of pulse you are getting with the controlled ISI, that is x and t is 1 for n equal to 0 and n equal to 1. Now we will see, we will plot this function, we will plot this function and understand this. Here in this function, here look at this Python function. Here I take, I import the SciPy and PyLab modules. SciPy is for scientific computing and PyLab is for plotting and visualization rather. So here I take t as 5, so w becomes 1 by 2t. And I take the time from minus 3t to minus 4t with an increment of 0.001. And I take the frequency domain, that is from minus w to w with an increment of 0.001. And I compute this function x small x, that is sinc 2wt plus sinc 2wt minus 0.5. And this I can run this. I run in the IPython 3, I run now you can see this is a pulse I am getting. Okay, this is a pulse I am getting, that is xt is sinc 2wt plus sinc 2wt minus 0.5. You get a pulse like this. Here you can see that the zero crossings are at minus 5 and plus 10 here. And this is the kind of spectrum we are getting. This is capital F. This is the kind of spectrum we are getting. So this is from minus 0.1, that is 1 by 2w. That is from minus w to w. Okay, this is value is 0.2. Okay, width is t is 5. So this width, this is from minus 0.1 to plus 0.1 with a width of 0.2. So this is the pulse we are getting. Let me go back to my presentation. So this is the thing we have observed. This is a this is called a duobinary signal. This xt, that's equal to sinc 2wt plus sinc 2wt minus 0.5. That is called the duobinary signal, and this is the spectrum of the duobinary signal. And now I can have a modified duobinary signal, that is with a different condition. This is also a relaxed case with x and t is 1 for n equal to minus 1 and minus 1 for n equal to 1 and 0 elsewhere. Okay, so I have two impulses, but one in the positive direction, that is n equal to minus 1, and one in the negative direction for n equal to 1. So the corresponding pulse becomes xt equal to sinc t plus t by t minus sinc t minus t by t. So this signal and spectra will be like this. Let us look into this Python code. This mode duo. Here also I put t equal to 5, and this is my w, that is 1 by 2t, and this is the time axis, that is minus 3t to 4t with an increment of 0.001. And this is a frequency domain, that is from minus w to w with an increment of 0.001. And this is my duobinary signal, rather modified duobinary signal, that is sinc t plus t by 2 t minus sinc t minus t by t. So this division by t I achieved with this negative power t raised to minus 1. And this is the value of capital XF, that is absolute value of value of this into sine pi f divided by sine pi f. So I plot this. Here I run. Here you can see that here this is my modified duobinary pulse, and this is the spectrum of the pulse. Okay, this is the spectrum of the pulse with a total width of minus 0.1 to 0.1 with a 0 in the middle. Okay, at f equal to 0 I have a 0 here. So this is a modified duobinary signal. And this is how we demonstrate that. And this is a modified duobinary signal and spectrum. And another concept in this before winding up is the I pattern. So the amount of intersimple interference and noise in a digital communication system can be viewed on an oscilloscope. The received signal yt, we see, you remember the old diagram, in that received signal yt, that you can display on the vertical input of the oscilloscope with a sweep rate set at 1 by t. So the resulting oscilloscope display is called an I pattern. So this I pattern looks like this. So this is a I pattern. This is the optimum sampling time this is happening. This is how the distortion happens. Distortion of zero crossings. So what ISI causes is ISI causes this I to close. Okay. So this is a kind of noise margin we see. So what happens is when the I closes, AWGN can cause errors in the reception. So this is a concept of an I pattern. Now coming to the end, you understood the design of duobinary and modified duobinary signals with the controlled ISI. And that's the end of this presentation. I thank you all.